Okay, so let us once again begin with a quick recap of what we have been talking about. Okay, so in the area of soft decoders, I was talking about how you can use the code words of the dual code to do decoding. Okay, so that is the main idea. Okay, so that idea I think is central to understanding these many decoders that we will describe from now on. Okay, code words of the dual are used to decode. Okay, so this is very important. Okay, so not necessarily the linearly independent code words in the parity-check matrix, but any code word of the dual can give you information about say one particular bit of the code word that you are interested in. Okay, so usually if you think of a code, okay, so if you think of a received vector R, okay, so you have R1, R2 through Rn, and suppose you want to somehow from this vector R get, let us say, the a posteriori LLR for the bit, for the first bit. Okay, so you are interested in terms like capital L1. Okay, so this is basically a posteriori probability for LLR, right? It is not just probability, a posteriori LLR for the first bit of the code word. We saw a description of how this can be expressed in terms of the individual scalar LLRs. Okay, so this is like the vector LLR, right? So this is basically log of probability that the first bit is 0 given the entire received vector R divided by probability that the first bit is 1 given the entire received vector R. Okay, so you can write an expression involving the small li's for a capital L1, and I described how to do that accurately, and that is a big nasty expression. A useful way of simplifying that is to look at code words of the dual. Okay, so each code word of the dual which involves bit 1. Okay, what do I mean by saying involves bit 1? In the first position it should be 1. Okay, so if you have any code word of the dual which has a 1 in the first position, that can be used to get some extrinsic information about the first bit. Okay, so the idea was to write this in terms of L1 plus extrinsic, and then you split this extrinsic information over every code word of the dual which involves the first bit or which checks the first bit. That is the idea. Okay, so if you have a code word of the dual, let us say let us say C prime 1, C prime 2, C prime n is the code word of the dual. Okay, then we know that the transmitted code word C dot C perp was 0. Okay, or what is true, C1 C1 prime plus C2 C2 prime plus so on till Cn Cn prime is 0. Now remember I said C1 prime has to be equal to 1. Okay, so this guy is equal to 1. So I have C1 plus then C1 C prime will be 1 in certain positions. Okay, it will be 0 in some other positions. Okay, so maybe you can say C prime I equals 1 for I equals I1, I2, so on. Okay, so let us say some IW. Okay, so there are W1s in C prime. Of course, I1 is equal to 1. Okay, so the remaining ones are also 1. So if you plug this into this equation, you would get C1 equals what? Ci2 XOR Ci3 XOR so on till Ciw. Okay, so every code word of the dual which has C prime 1 equal to 1 gives you a parity check equation involving C1. Okay, so this can be used for getting extrinsic information. Okay, so this is a bit of a crucial idea in many decoders. Okay, so you have the entire code word, you have the entire received vector R. Okay, of course I can split my a posteriori LLR as the intrinsic L1 plus some extrinsic information, and this is going to be a extrinsic information is going to be a big complicated expression if you want to evaluate it exactly. Okay, but approximate evaluations usually involve looking at code words of the dual which have C1 prime equal to 1. Okay, the first position should be 1 at in the dual. If that is the case, then if you look at the condition that is satisfied between the code and the dual, okay, so you know C dot C prime has to be 0, that gives you some equation involving C1. Okay, so if you use this to provide extrinsic information, it is going to be a simpler operation to deal with as opposed to looking at the entire expression and trying to evaluate it. You can try and attack it this way. Okay, so now the idea is to look at multiple code words in the dual and see when you get independent extrinsic information. As long as you keep getting independent extrinsic information, you can keep adding the extrinsic LLRs. Okay, the trouble is you can't really keep track of everything there. Okay, eventually you will also get some dependent information. How do you deal with that is the question. Okay, so the various approximate decoders do various tricks. Standard trick is to simply assume independence even if it is not there. Okay, so that this is the basic general principle behind approximate iterative decoders for at least Ldpc codes. Okay, so in general also this is the philosophy. This is very useful to keep in mind. Okay, so the only kind of remaining detail here, if you're going to do this, you know how to get this extrinsic information, right? Given this equation, it's the 2 tan hyperbolic inverse tan hyperbolic product. It's very straightforward to get the extrinsic information from here. The only remaining information is from the dual. Okay, what are the code words from the dual that I should consider, and in what sequence? Okay, which one should I consider first, which one should I consider next, etc. Okay, so that's essentially the problem that's left here. Okay, all right. So this is where we kind of stopped for the soft decoders. But remember, I mean this can be actually done for any decoder. It need not necessarily be soft or anything. Okay, so even if you had even if your received vector R is just bits, it's over the binary symmetric channel. Okay, you're getting only bits. Maybe you can't think of a log likelihood ratio. In fact, you can think of that also, but maybe you don't want to think of a log likelihood ratio. But nevertheless, you can use these equations for doing decoding, even for the binary symmetric channel, because this is a valid equation for any channel. Okay, so if you look at these bits, the bits on the right hand side, they will give you some information about the first bit. Okay, so the principle to remember is you want dual code words of low weight. Why do we need low weight? Yeah, so then this extrinsic information is more meaningful. Okay, so as you keep increasing the weight, extrinsic information will be 0. If weight becomes very large, extrinsic information will be 0 and you don't get anything. Okay, you want it to be non-zero, and if it has to be non-zero, it's much more likely to be non-zero if you have lower weight. That's the main idea here. Okay, so you want low weight dual code words, and like I pointed out, you can use it for any decoding. Even if you have a hard decision decoder, you can use such things. That's the other point maybe which I did not emphasize. We saw it in the context of soft decoders, but even if you have hard decoders, you can use this equation in the hard decoding. Okay, and then the third crucial point is independence. Okay, so you don't want the dual code words to overlap in any other position other than in the first position. Okay, so these I1s are the I2 to IW, right? If you look at another code word, they should not be the same. I1 can be 1, but there should be no overlap. If there is no overlap, then you will have independent information and you can keep on adding without any problem. Okay, so these are general principles which are quite useful to keep in mind. So when I describe the decoder, if you keep these principles in mind, some of the steps will make sense. Okay, otherwise it will seem like it's just an ad hoc decoder that people have come up with. Okay, all right. So any questions on any of this? Is it okay? Seems clear. Okay, good. All right. So the next thing we saw was the definition of low density parity check codes, and Okay. So, in particular I spoke about regular low density parity check codes. Okay. So, these are parameterized by two quantities, the WC which is the column weight and WR is the constant row weight. So, these codes basically have sparse parity check matrices. Okay. And in particular one type of code is the regular code, where each column has WC ones and each row has WR ones. Okay. So, if your block length is n, then your parity check matrix will actually be a n times WC by WR times or cross n matrix by n matrix. Is that okay? This will be the number of rows. This quantity here is the number of rows, and you can show that. It is not too difficult. And there are many ways of constructing it. One method is Gallagher's construction, which works if WR itself divides n. Okay, there is a way of splitting the matrix into WR parts and picking each one in an obvious way and then doing arbitrary permutations. Okay. So, crucial thing to remember is this is not unique. Okay. So, it is in fact if you say a regular LDPC code, you are not talking about one code. Okay. So, you are talking about in fact an ensemble of codes. Okay. So, this is actually an ensemble of matrices. Okay. So, we will see later that these ensemble of matrices share some properties, particularly under certain types of decoding, they share some good properties. So, it makes sense to think of them together as one ensemble. Okay. So, from a design point of view, important issues are what values should you take for WR and WC, etc. One parameter there is the design rate, which is simply 1 minus WC by WR. It turns out the rate of the code is always greater than or equal to design rate. Okay, how did this come about? The number of rows is of course n WC by WR, which means the rank is less than or equal to n WC by WR. Rank is n minus k, so k is greater than or equal to n minus n WC by WR. So, rate is greater than or equal to 1 minus WC by WR. Yes. Okay, so the question was basically, can the design rate be negative? Okay, from purely a matrix point of view, yeah, it can be negative. Okay, but from a code point of view, maybe it does not make too much sense to have it as negative. Okay. Usually, yes. So, if your rate is usually positive, right? So,
but then it doesn't violate anything.
Yeah, actually it is also possible. So, that is the other part of the issue. Even if your design rate is negative, the rank can at most be n, right? At least, I mean, not at most be n, yeah, it cannot be greater than n. So, it might end up being an invertible matrix, in which case the code is just the trivial all 0 code. That is the only danger. Or maybe the rank is less than n, in which case the actual rate might still be positive. Okay, all right. So, that is why this word design rate is a bit misleading, but that is the best thing that you can come up with. But what will happen is, if your WC and WR are small, okay, say for instance 3 and 6, WC is 3, WR is 6, you construct a random matrix like that. In the Gallagher construction, you will see that there will be exactly 2 linearly dependent rows, nothing more than 2 will be linearly dependent. Okay. So, you can see very easily in the construction, the way we construct, there will be at least 2 rows which are linearly dependent on the others. Okay. So, if you think about it, if you add up everything in the first section, you get the all ones. In the next section also you get all ones, etc. So, that is for WR equals WC equals 3. Okay. So, you get 2 which are linearly dependent, nothing else will be linearly dependent. You can see that also, mostly in a random construction it is very difficult to get linearly dependent rows unless you do some very basic things. Okay. So, the next crucial idea is this notion of a Tanner graph. Tanner graph is a graphical representation of parity check matrix. Okay. So, the idea is we have a bipartite graph. On the left nodes, the nodes are called bit nodes. These are also sometimes called variable nodes, but we will use bit nodes almost exclusively. So, you can in fact number them if you like from 1 to n, there will be n of them, and on the right side you have nodes that are called check nodes. Okay, if you number them from 1 on, you will get, for the regular codes, you will get NWC by WR of them, and the edges you put basically are, they represent ones in the parity check matrix. Okay, so, if you go to the first row will contain ones in certain positions, certain bits, certain bit positions. You simply connect all those bit positions to this. Okay, so, that is the Tanner graph. Okay. So, some things to keep in mind here. Okay, so, this each node is said to have a certain degree in this graphical representation. Okay, so, what is the degree? Degree of a node is, okay, this equals the number of edges incident on it or connected to it. Okay. So, what will be the degree of a bit node in a Tanner graph? It will be equal to WC, right. What will be the degree of the check node? It will be WR. Okay. So, that is something that you can see very easily. So, based on the Tanner graph, you can come up with something known as a socket construction for regular ensembles, where for each node you have as many sockets as its degree. Okay. So, on the left side you would have WC sockets for each node, on the right side you would have WR sockets for each node. Okay. In total you would have n times WC sockets on both the left side and the right side if you add up everything, and then you define a permutation of NWC numbers from 1 to NWC. That tells you a way of connecting the edges, and it maintains the degree constraint, right. Every node will have, every left node will have exactly degree WC, every right node will have exactly degree WR. Okay. The only confusion there is two nodes, one bit node and one check node might have more than one edge. Okay. So, you should have some way of resolving that. There are many ways of resolving it. For instance, you could say if there are more than one edge, I will maybe drop one edge or something like that. So, you can come up with something like that, it does not really matter. Or another thing to do is to say I will only look at those permutations which do not give me multiple edges between two nodes. You could say that. If you say that, then it will map properly to a parity check matrix, otherwise it will map to multiple parity check matrices or something, but it is not a big deal, you do not have to worry about it. You can show that an overwhelmingly large number of permutations will not give you multiple edges, so it does not really matter in practice. Okay. All right. So, that is about constructions, Gallagher's construction and the socket construction. So why the Tanner graph? Okay, so you might say, okay, the parity check matrix itself has all this information, why do I need to go to the Tanner graph? Okay. So, it turns out the decoder that we will be considering for Ldpc codes, which works really well and provides all capacity achieving performance, etc., is described usually on the Tanner graph. Okay. So, you remember I was talking about suboptimal decoders just a little while ago. I was saying you have only thing that you have to specify is what code words of the dual are you looking at and in what sequence, right. So, that is what you have to specify, right, in a way. In a suboptimal decoder you are going to look at one code word of the dual at a time. So, which code words do you want to look at and in what sequence, etc., has to be specified. It turns out the Tanner graph helps in the specification in a very efficient way. Okay. So that is the main utility of the tanagraph. The decoders are described very nicely in the tanagraph. Okay, other than that, it's just an entity. Of course, today there are a lot of there is a general area called inference in graphical models. Okay, so it's a very popular area. A lot of people are doing work on it. It has connections to statistical mechanics, statistical physics, statistical physics, and information theory. So many other connections are there. So of course, the graph itself has a lot of importance. Okay, I'm not saying it doesn't have importance, but for us, at least in the first course, we will be just concerned with how it represents the parity check matrix and how it specifies the sequence at which you are looking at code words of the dual in the decoder. Okay, so that is the thing that will be interesting to us. Okay, so we have seen the definition of low density parity check codes. We have seen how to construct them. Okay, so at least technically we have seen how to construct them. You can write a MATLAB program or a C program to do the construction, given a WC and a WR. Okay, the next most crucial step, well, the most crucial step is the decoding, but before that, let us quickly see encoding and get rid of it, and then we will see how decoding needs to work out. Okay, so encoding is really nothing much to say about encoders. I will mention them very briefly. So you have a parity check matrix, okay, from the, let us say H is from the NWCWR ensemble. Okay, I should also point out that the regular codes are not the, I mean, there are many more LDPC codes than just regular codes. Okay, so there are all kinds of sparse matrices that do not respect regularity, and there is a lot of benefit in going to irregular codes also. Okay, codes that are not regular, but for now we will see regular codes for a while, and then later on we will move to irregular codes. Okay, so suppose you have a parity check matrix from the NWCWR ensemble. How will you go about designing an encoder for the code? What will you do? What is one? Yeah, one is to find the generator matrix. Exactly. I mean, that is the method, right? So how will you find the generator matrix? Yeah, so you have to convert the parity check matrix to the standard form, the systematic form. Okay, so you do row operations and convert the parity check matrix to systematic form. What form would that be? Let us say Pi. Okay, and after this you can use the matrix P to do encoding. So how will you do encoding? If you have a message M which is k bits, you are going to say the code word is what? M and then MP transpose, right? So that's it. That's the encoding. That works out. Okay, so this gives you a valid code word, and you can do this. But the only trick here is, only problem, so to speak, here is how complex is this encoding. Okay, so how many operations does it take as a function of n, for instance. Okay, you would like it to be a linear function in n. Okay, for every code word that you are putting out, you would like to do the same amount of work, so to speak. Okay, so you don't want to do a constant amount of work. Okay, so you don't want to do too much more work. But it turns out when you do row operations, the sparse character will be lost. Okay, so as row operations involve adding a lot of rows, you have just WR rows, which might be a very small, but WR ones in each row, which might be a very small number. But when you keep doing row operations, you are going to increase that number a lot. Okay, so this P in general will be a dense matrix. Okay, it will be dense, but it is not too scary, because what is the size of P? Size of P is simply n minus k cross k, right? So at most it is going to be n squared or something. Okay, so there will be n squared ones, maximum number of ones that are in P can be about n squared. Okay, so the complexity of this encoder can go as much as n cubed. Okay, n cubed, exactly, something like that. So roughly n cubed complexity you will face in this encoding. Okay, so it turns out you can do something smarter. Okay, so instead of doing row operations where you are adding rows, which is what causes increase in the weight, right? If you only do row swaps and column swaps, then you are not increasing the weight of any row, you are not changing the sparse character of the matrix. Okay. So, there are efficient algorithms to do only row swaps and column swaps and convert parity check matrix to some other form which looks similar to this. Okay. So, there is efficient encoding methods. I am going to do something. Let me talk about that. Okay, so, the first thing you can try is, so there was a question about maybe you can change the design of H to force some constraints on it. We will come to that soon enough, but before that, one way to fix this n cubed complexity is to say that I will do from H row swaps and column swaps, and then maybe I will get a matrix of the form some P and then some T, where this T is some triangular matrix. Okay. It may not be fully triangular, maybe some small part of it, some small delta part of it might be dense for some reason. You might have to, I mean, to make it fully triangular, you might have to live with a small dense part for the matrix, but except for that small dense part, most of the other parts were done purely by row swaps and column swaps. So, the weight did not increase in some significant fashion. Okay. So, in fact, you can do this and you can show that the complexity here can be at most linear. Okay. So, this would have complexity. So, when I say complexity, I am talking about the number of operations. Okay. So, how many bit XORs you have to do to finish the encoding. Okay. So, it is going to be of the order of n power 3 here. So, you can do this smartly. Okay. There are papers that have been written, you can write programs based on those papers and do it very, very smartly and make this delta really, really small. So, except for a very small tiny part of your matrix, everything else is sparse and you have this P and upper triangular nature. So, it is very, very easy to do a inverse in this format, and you can do encoding with this also. You can put your message here, find the last bit, then do a back calculation. Since only a small part is dense, the back calculation will be done very quickly. Okay. So, that is the idea. So, you can do this and then the complexity here becomes roughly n. Okay. So, almost linear. Okay. So, that is one way to solve the problem at the encoding side. The other problem is what was suggested. Okay. The other suggestion was maybe you can design H in a very smart way to make encoding easier. Okay. So, that is actually what is done in many standards today. Standards accept Ldpc codes which have a very simple encoder for the simple encoder based on the structure of the parity check matrix. Okay. So, it is a little bit more complicated, maybe towards the end I will describe how that is done. Okay. So, for now this is a better situation to keep in mind. Okay. The main idea is, given a parity check matrix, anyway you can come up with an encoder if you do not care too much about having a little bit more complexity. N cubed is not so scary, it is still polynomial. Okay. You can do it very easily, that is not a problem. But even if you are worried about linear complexity, there are methods, very standard methods which I am not describing here, but they do exist, which will help you simplify this encoder because of the sparse nature. Okay. So, you are doing some smart swaps and column swaps to get rid of this. Alright. So, this is all I want to say about encoding. As you can imagine, encoding is a simple problem. Okay. So, it is not really that complicated. Even when we saw before, we never spent too much time discussing encoders because it is reasonably simple, we can do it often. Relatively much more complex problem is the decoder, which is what we have to spend more time on. Okay. Any questions on this? Everybody is okay, particularly after I said it is not important, nobody is going to ask questions on something like this. Okay. Alright. So, that is all I wanted to say about encoding. So, now so what can we do now? So, if you want to summarize, we can construct Ldpc matrices. Okay. And what kind of Ldpc matrices? N WR, WC WR, right? Let us say N WC WR, we know how to construct. Okay. And usually, as you can imagine, you would keep these two constant, okay, these two very small, or when I say constant, it is always independent of n. Okay. That is what I mean when I say constant. Okay. So, functions of n and independent of n. So, these would be relatively small. A very standard choice would be to put WC equals 3 and then WR would be 3 by 1 minus rate, okay, the rate that you want. Okay. So, is that correct? Yeah. Okay. Rate is, so this is a very standard choice. This is okay. That's correct, no? Okay. And then you would increase n would be, let us say 100 to start off with, and then if you see that is not good enough, you might want to go to 1000, and then you might want to go to 10,000, etc. Okay. So, this is how you construct and try out these codes. So, when I say construct, you are not going to construct all possible matrices out there, some random instance of this ensemble. Okay. So, you are going to just pick the column weights randomly, row weights randomly, and hope that you get one random member of this ensemble, which is good. Okay. So, that is the idea here. All right. So, you have to write computer programs for this. It is not just sitting down with a pen and paper and constructing this. There is no way in which you can do this, right. 10,000 with 3 and 3, it is not going to work. Okay. You are not going to be able to do that, but still it will be efficient, as in many of these matrices are sparse, and many computer programs, many like even MATLAB has a lot of algorithms for sparse matrices. For storing them, you do not have to, for instance, if it is a 5000 by 10,000 matrix, that is a lot of entries, but you do not have to store every single entry, you know, it is sparse. So, you only store the locations and the values of the non-zero entries. So, storage is efficient and all that. So, you have to do all that in your program, okay, only then it will work, otherwise you need some 16 gig or 32 gig machine of RAM to make things work, and it may not be efficient. Okay. So, it is easy to write programs, given that you are careful with memory in some high level way. If you are careful, it is okay. Okay. The next thing is we can encode, there is no problem. Okay. So, using some standard ideas. So, of course, the most crucial part is decoders. Okay. So, what is it about these low density parity check matrices is that there should be something, right, they are so popular, some crucial property that they have that gives you very efficient decoders is the main study here. Okay. So, what I am going to do is basically I am going to describe decoders for the binary symmetric channel first. Okay. There are various approaches you can take to this describing the decoders, you can do it in so many different ways, but what I found to work very well based on past years is to first describe the decoder for the binary symmetric channel. Okay. It will be a suboptimal decoder. It will use the principle of looking at code words of the dual through the Tanner graph and then getting some information about every bit. Okay. So, it will be bitwise, it will be suboptimal, and it will use the Tanner graph. Okay. So, those are the generic properties, and this decoder, the first decoder I am going to describe was actually given by Gallagher himself in the first in his thesis. It is called Gallagher A decoder for the BSc. Okay. When I say Gallagher A, it is automatically assumed that it is for the BSc. Okay. So, what kind of a picture are we looking at now? The binary symmetric channel and the Gallagher A decoder. Okay. So, you have a message M which gets encoded by a let us say CWR Ldpc code, regular Ldpc code. You get a code word C, it goes through a binary symmetric channel with, let us say, a transition probability P, and then you are going to run this decoder on the received vector R, which will now be bits. Okay. So, all of these things will be bits. Okay. You will be running your decoder on this. Okay. And this will produce C1 cap, C2 cap, so on. Okay. Like I said, all these things will be bitwise, it will work like this. Okay. So, this decoder is clearly what is called a hard decision decoder, it is not a soft decision decoder. We will see soft decision decoders soon enough. After we finish this, after we analyze this and understand it, we will move towards soft decision decoders as well. Okay. But there are so many general principles behind this decoder, it will take a lot of time to describe it also. Okay. So, we have to go through it very slowly. Alright. So, this is the setup. So, when I say received vector R now, I am going to say R1, R2 through Rn, but each Ri is a bit 0 or 1. obtained when a code word C was transmitted through a binary symmetric channel with transition probability P. Okay. So what's interesting here is, so when Gallagher wrote his thesis, he did not mention tanagraphs. Okay, so his description of the decoder was always through the parity check matrix. So what I am going to do next is to first describe the decoder through the parity check matrix, then look at the corresponding tanagraph interpretation, and you will see that the tanagraph interpretation is very natural and nice and can be extended very nicely. It gives you a feel for what's happening. Okay, so even the parity check matrix is probably good, but the tanagraph makes it much better to understand what happens. Okay, so what are we given now? We are given a received vector R, R1, R2, Rn, and then we know that the code word that was transmitted satisfied several parity check equations given by the parity check matrix H. Okay, what else do we know? This comes from a WC WR ensemble. Okay. So if I want to decode the first bit C1, okay, remember when I do bitwise decoding, there is intrinsic and extrinsic information. What is the intrinsic information that I have about C1? It's R1, right? R1 is a bit itself. Okay, C1 is equal to R1 with probability 1 minus P, and it is not R1 with probability P, and P is less than half. So with a higher probability, it is going to be equal to R1. Okay, so the intrinsic information is simply R1. Okay, all right. So the bit R1 itself is the intrinsic information, so to speak. Okay, and then now I have to worry about what kind of extrinsic information I can get about C1 from the code words of the dual. Okay, right. And what do I need? I need code words from the dual which have a 1 at the first position. Okay, just by staring at the parity check matrix, how many code words can I come up with immediately? Let us say in the first round, right, first iteration, first round, what are the parity checks that you can come up with immediately? WC of them you can come up with. What are the WC of them? Wherever you have ones at the first column. Okay, so I know in the first column there will be a bunch of zeros, and then there will be a 1, and then there will be another 1, then there will be another 1. Okay, in my illustrations I will assume WC is 3, for instance, just to keep it simple. So you have 3 ones here. Okay, that will be in general WC ones, and those WC parity checks, those corresponding rows, will definitely give you extrinsic information about C1. Okay, all right. So let us say the first one that you take here has a 1 in position, let us say I1, I2, okay, and then it has a 1 in position I3, so on till 1 in position it should be actually WR minus WR, right, then it will have 0 elsewhere. Okay, there are WR ones like that. Okay, and what information does this give me? This thing is telling me C1 XOR CI2 XOR so on till CIWR was actually equal to 0. Okay, so from this equation, what extrinsic information can I get about C1 from RI2 or IWR is the question. Okay, so remember these are all hard decisions now. When it was soft decision, I had to worry about probability and all that. When it is hard decisions, I cannot do anything more. The only thing I can say is extrinsic information from this equation, for instance, is simply what? There is another estimate for C1, which is simply RI2 XOR RI3 XOR RIWR. Okay. The intrinsic information is giving me one estimate for C1, which is R1 itself. Okay. The first extrinsic information I am looking at, first parity check I am looking at, gives me one more estimate for the same bit C1. It is telling me the C1 can also be equal to Ri2 plus Ri3 plus so on till Riwr. Okay. So remember C1 was equal to R1 with probability 1 minus P. What is the corresponding probability here? With what probability will C1 be equal to this guy?
You will have to take all combinations.
Right? See, be very careful here. I am now XORing WR minus 1 other bits which each of them could be in error with probability P independently. Okay. If an even number of them became in error, then I am okay, my C1 is still going to be okay, my estimate is going to be okay, but if an odd number of them are in error, then my estimate is wrong. So the only probability I have to look at is out of WR minus 1 bits, what is the probability that an odd number of them will be in error, given that each one of them is independently in error with probability P. Okay, so that is a calculation you can do with the binomial expression and so on. You will see that the probability will work out to something like 1, I think it is 1 minus or 1 plus, it should be 1 minus, I think it should be 1 minus, but 1 minus 2p power WR minus 1 by 2. Okay, so this is the probability of correctness of this. This is simply 1 minus p. Is it 1? I think it is plus, man. This should be plus, no? So you want an even number of errors, so the odds should go away, so I should add. It is correct, right? P is 0, it should be 1. I am looking at probability of correct decision. It is okay, is that fine? So this is the probability with which this estimate is correct. Okay. Now I am going to look at the next row that I have here. Remember I have WC rows. Okay. Now what will happen in the next row? Okay. So this next row will now have, let us say, 1 in the J2 and then some other one here, J3, so on till the last one maybe is in JWR. Okay. Okay. So I have deliberately put these ones even in this picture in a certain way. What is it that I have done? Yeah, I am picking them to be different from I2, I3, I omega r. Okay, so that is the crucial idea here. So now if the second equation had ones in positions which did not overlap with the ones of the previous check that I used, then that equation that I get will give me an estimate which is statistically independent from both the previous estimates I had. Okay. R1 is clearly statistically independent of all these guys, and then the next estimate will also be statistically independent. Okay. So likewise I will get how many estimates in the first round immediately, I will get WC estimates. Okay. So that is the first step in the decoding. Okay. So you could call it the row step, or so the first half iteration looks at rows of the parity check matrix and generates estimates for the bit. Okay. Then now the next half of the iteration will try to process all these estimates and come up with some better final estimate for the bit. Okay, that's the split. All right. So this step is clear, right? The row step is clear. You look at each row, then try and come up with an estimate for the particular bit that you are interested in, C1. Okay. Yes. So that's the next question. Okay. So of course, now so okay, the question was, should you construct H so that this condition is satisfied? Yes, absolutely, definitely. It would help, right? So second row should not overlap with the first row here in any position. So that is one of the crucial constructions, crucial conditions imposed on the construction. Okay. So the 3 rows that you have corresponding to the first position, or in general the WC rows you have in the first position, will definitely overlap in the first position, can't do anything about it, but they should not overlap anywhere else, so that the estimates you are getting end up being independent, and that is nice. Okay. So as we go along, as we do the decoding, you will see there are some nice conditions like this that will come, and we have to enforce them in the construction. Okay. So far we just said construction is every matrix we will pick, but maybe you should not pick every matrix, you should enforce some smart condition like this to get better decoders. Okay, so the row step is clear, right? So let me describe the steps kind of informally, and then finally I will write it down. Okay, when I write it down, I will write the complete expression, but you will see that that is much easier to write in the Tanner graph than in the Parity-Check matrix. Parity-Check matrix is a little bit more confusing to write. Okay, so the row step is clear. So now the next thing to remember is, what will I do for C2? Yeah, just look at the corresponding column for C2 and repeat the same steps. Okay, for C3 again do the same thing, C4 again do the same thing. So in fact you can do this step for all the bits at the same time if you like, if you have enough memory. You can do this operation in parallel, and in fact you can also save a lot of these operations. Okay, so if you look at CI2, you know, that also involves the computation of the same parity check. So you can do that computation first and then update all the bits that it was involved in, for instance. You can do it very smartly if you like, or you can do it sequentially, bit after bit, evaluate all the checks and can figure out what happens. Okay, so there are various ways of implementing it, that is the detail, but you have to do it for all the bits. Okay, alright. So I have been saying that this is like the first half of the first iteration, okay, and then you have the second half of the second iteration, and then there will be multiple iterations. Okay, so you will see what happens there later on. Is that okay? So at the end of the first half of the first iteration, you have WC estimates, or how many estimates exactly? WC plus 1 estimates for each bit. Is that okay? You have WC plus 1 estimate. What is the plus 1 from? The intrinsic estimate. Okay, so you have WC extrinsic estimates. Okay, WC extrinsic estimates, and you have one intrinsic estimate for each bit at the end of the first iteration. Okay. So the intrinsic one is very easy. So each of these estimates you might want to call them something. Okay, so for instance you might want to call them okay, so we will come to that later if you like, but maybe it is useful. So let me say each estimate WC of them, these things are, maybe we denote them as U, what is a good notation, man? So I want to put 1 here to indicate iteration, and then 1 here to indicate the bit position, and this is the extrinsic information. Okay, so this is not U2, still U1. Okay, so this is how I will denote the estimates that I am getting. Okay, the intrinsic estimate is simply R1. The first extrinsic estimate I am getting about the first bit in the first iteration is U, superscript is for the iteration number. In the subscript there are 2 of them. The first subscript denotes the bit position itself, the second subscript denotes the number of the extrinsic information, number of the row. The first one will give you the first one, second one, so on. Okay. So at the end of the first half of first iteration, okay, of course you have the intrinsic estimates R1, R2, Rn, and then you also have all these extrinsic estimates, right? U1, I1, U1, I2 all the way to U1, IWC for I from 1 to n. Okay. And if you took care of the constraint, what is the constraint? The rows of the parity check matrix do not overlap in more than one position. Okay. So that is the generic constraint. If the rows of the parity check matrix do not overlap in more than one position, then all these estimates will be in fact independent for each bit. Okay. So these things are independent if no 2 rows of H overlap in more than one position. When I say overlap, it basically overlap in ones. Okay, of course they will overlap in zeros, and we do not care. Okay, they do not in more than one position. Okay. So, if you take care of this constraint, then this will be independent, right. So, in the second half of the first iteration, so the first half of the first half is always called row processing. Clearly the rows of the parity check matrix are involved, so it is called row processing. The second half is called the column processing. Okay, so let us see what you can do in the second half. Okay, so which is also called column processing. Okay. So, what can we do? So, let us look at the first position. So, let us look at the first position, we will fix I equals 1. You of course have R1, and then you have U11, so on till U1 1 WC. Okay. So, let us just empirically look at this situation. Which of these estimates is most reliable? R1, right. So, you can't make anything better than R1. Okay. So, R1 is definitely your best estimate. Any XORing you do will definitely be poorer than 1 minus p in success probability. You can show that if you want. I mean, it's intuitively kind of clear. You're XORing more than one bit, it's going to be bad. Depends on the weight, of course. If WR is equal to 2, then I guess you will get one more of equal reliability, but it can never be greater than R1. Okay, but usually WR is not going to be 2. Okay, WC is going to be 3. WR will be some 6 or something. So it's going to be larger, and it will always be poorer. Okay, so you have to, in your column processing, rely a little bit more on R1 than you rely on the other things. Okay, so you can now come up with several ad hoc methods. The method that is described as Gallagher A is the following. Okay, so what I am going to describe next is the Gallagher A processing for columns. Okay, second half of the first iteration. Okay, so what you will do is, if U111 equals U112 and they are all equal, all these estimates are, let us say, equal to some b, then what? Okay. Okay, so let me just make sure I get this absolutely right, because it can be, it's a bit dicey to explain it, so I should do it very carefully. Okay, so let me just maybe step back a little bit before I do this and say, okay, so let me step back before this. Okay, so let me not describe this first. Okay, so there are two things that you have to do first. Okay, so in the column processing there are two parts. Okay, so there are two parts to column processing. The first part is the easy part. First part is making decisions. Okay, which is very easy. Okay, so this part is easy, and then the second part is preparing for the next iteration, right. Okay, so this part is a little bit more tricky. Okay, so what I started to describe was actually the second part. So, but before that I should tell you what the first part is. Okay, only then you will be happy. Okay, so let us say C hat 1 is some kind of decision we make on the first bit. Okay, so this can simply be majority of, Okay. So, this is one way of doing it. You can say this is simply majority of R1 U1 1 etc. Okay. You could do this. Okay. So, this is not too difficult, or if you want you can give some more emphasis to R1. You can say if R1 I would give more weightage to R1 etc. So, you can do this in multiple ways. It turns out this is not very crucial. So, the making decisions is very easy. Okay. So, you repeat for Ci1. Okay. So, that is the first part. You simply make a decision, but if you were to stop at the first iteration, believe me, your decoding will not be very successful. Okay. So, you are not going to get much more. The crucial thing is to doing is the second part, by which you do multiple iterations. Okay. So, for doing the multiple iterations with the matrix, I will try and describe it. It is only a first shot at the description. It is going to be confusing to you, but then later on I will say I will do the same description with the Tanner graph, and you will see in the Tanner graph the description becomes very smooth and simple. Okay. So, even if you do not understand it, stay with me for a while. I will quickly go through the description here in with the matrix point of view, because I think you should see it once so that you get a feel for what is really happening. Okay. So, in the second part, when you prepare for the next iteration, remember what has to happen in the first half of the next iteration. You have to do row processing, which means each row should now have some estimate of what the connected bit was, right. In each row, how do you do the processing? You simply take the r's and you add it up, but the r itself was used in the first iteration. In the second iteration, you have to do something slightly better. Okay. You can't repeat the same r. If you repeat the same r, you will simply be doing the same thing again and again, you won't get anything new. Okay. So, what you have to do is, in this, instead of these r's, you have to use better estimates for Ci2. Okay. In the first iteration, I would have got some estimate for Ci2, okay, which used Ri2 and some other information. So, that estimate I have to use here. Okay. So, that is the main idea. Okay. So, I have to use some better estimate for Ci2 than simply Ri2. Initially, I used it because that is what I got from the channel. I did not have anything else, so I used it initially. In the first half of the next iteration, I should use a better estimate for Ci2 in each of these equations. Okay. So, the duty of the second part of the second half of the first iteration is to simply come up with what estimates to use for each bit in the next step. Okay. So, it turns out you should not use the same estimate for every single row. Okay. So, remember, if you go back and look at this, initially in the first iteration in the row processing, you simply used R1 for every row that C1 was involved in. So, let me go to I2 for instance. Maybe I2 was involved in 3 rows. Okay. You use the same Ri2 for each of these 3 rows as an estimate. It turns out in the next iteration you have to use a different estimate here and a different estimate here and a different estimate here. Okay. So, it is not a good idea to use the same estimate of Ci2 in all the 3 rows. In the first row you have to use an estimate of a different estimate of Ci2, the second row you have to use another estimate, the third row you have to use yet another estimate. Okay. In the first iteration, if I2 was involved in 3 rows, you use the same estimate Ri2 for each of those rows. In the next iteration, you have to use different estimates. The reason is, I will tell you why you have to do that. Okay. Suppose you want to figure out what better estimate to use for Ci2 in this particular row. Okay. Right. You have to use Ri2, then you have to use the estimates that you got from this second row and this third row only. You cannot use the estimate you got from this particular row once again. The reason is that will directly kill your independence assumptions. Okay. So, you want to keep successive estimates as independent as possible. See, suppose you use the estimate you got from this once again in a loop inside, you will be using the same thing over and over again, and you are passing it inside that same parity check, so to speak. So, you will have a lot of repetitions and it is not a good idea. Okay. So, this part is not very clear from the matrix point of view, but if you look at it from the Tanner graph point of view, it will be much more clear. Okay. So, it is not a good idea to use the same estimate for each row, okay. You have to use different estimates for each row, all right. So, it turns out beginning with the next iteration, each bit position will have one intrinsic information and it will have WC updated information that is used in the row processing, okay. It will have WC of them, not just one Ri2. You will use one estimate for the first row, another estimate for the second row, so on till the WCth row you will use another estimate, okay. So, those estimates we will denote as V what? V2 11, V2 12, so on till V2 1 WC. What is this guy? Estimate of C1 used in first row, right, in second iteration, okay. What is this one similarly? Estimate of C1 used in the second row in which it appears during the second iteration. So, likewise you have to keep repeating this, okay. So, in general you will also have what? Vi1 2, Vi2, so on till 2I WC, okay. So, we will have WC different estimates for each bit now, okay. So, the question in the second part of the second half of the first iteration is to figure out all these guys. You have to figure out what estimate to use in each row in the next iteration. Is that okay? So, finally, when I put everything together, maybe it will be a little bit more clear, okay. So, let us just do this, describe it, then I will come back and say how it is used, okay. So, how do you decide this is crucial, okay. So, how do you decide this? The way you decide so, the way you decide Vi1, so I will just describe how you decide Vi1, okay. If U1 I2 equals U1 I3 equals so on till U1 IWC equals some B, okay, right, then you will set V I12 to be equal to that B, okay, else you will simply set V I12 to be Ri itself. Okay. So, remember the ith bit got an intrinsic estimate which was Ri itself, and then it got WC extrinsic estimates. It got the first estimate from the first row, second estimate from the second row, and so on, okay. Now, to update the estimate for the first row, what are we doing? We are looking at the estimates from second row, third row onwards. We do not look at the estimate that you got from the first row itself, we look at the estimates you got from the second row, third row. If all those estimates agree and they are pointing in one direction, which is B, then you simply say the estimate I will use for my first row is that B. In case there is any disagreement, what do? You simply go back and rely on the intrinsic information for that particular value, okay. So, that is the idea here, okay. So, if you want, you can go back and look at this picture, this will be a little bit clearer here, okay. So, remember, if you now look at the I2th position, okay, you will get one intrinsic information Ri2, and then you will get one extrinsic information from this row, another from this row, another from this row. In the updated version for this row, what am I going to look at? I am going to look at these two extrinsic informations. If they agree, what will I do? I will set that as the updated value for I2 in this row. If they disagree, then I will say I will simply reuse RI2, that is the idea, because RI2 anyway was a good estimate, I know I can use it. Okay. So that is Gallagher A decoding algorithm, that is what Gallagher A decoding algorithm does. It is not best or it is not the greatest or anything, okay. So it is just an ad hoc method, that works a lot. There are some principles here which are very good, okay, that works very well, that is what I mean. Okay. Okay, so hopefully this is clear. Okay, so what will I do for Vi2? Okay, what will I do for Vi2? If Ui1 equals Ui3 and so on till Uiwc equals a particular bit, then I will set Vi2 to be equal to P, else this will again be Ri2. Alright, if you want we can go back once again to this picture. What is actually happening here is for the I2th bit, if I want to update this guy, okay, I will see the estimate that I got from the first row and the estimate that I got from the third row. If they agree, I will set the new value for this to be that agreed value, okay. Else I will simply reuse Ri2, okay. Alright, reasonably clear, okay, maybe. That is it, I mean that is all, we are done. I have described the entire decoder. What will you do in the next iteration? Maybe I should just describe the row processing for the second iteration. Oh, did I put Ri2? Yeah, it is just Ri, I am sorry. I am doing I here, sorry. Is that okay? So maybe I should describe row processing of iteration 2. Okay. What will happen in the row processing for iteration 2? Okay, if you want to look at the ith bit, you will compute U2 I1, U2 I2, so on till U2 IWC. How will you compute this guy? Okay, so it is a little bit tricky, right. So you will use new estimates for each bit corresponding to that particular row, alright. So for instance this one maybe, so originally it might have been connected to something, so you will have to use the new estimate. So let me set I equal to 1 for instance, okay. If I did that, U112, okay, how will this be computed? So remember what was my equation, C1 equals Ci2 plus Ci3 plus so on till Ciwc, okay. Now for the I2th bit, okay, I originally I used Ri2, okay, now I will be using Vi2. I do not know the number exactly, but I will be using something, okay. Okay, what is that number? Why did I put a question mark there? So I have to figure out in which row connected to I2 1 will occur, okay. So that is a bit more tricky, you have to write in the matrix properly, only then you will understand, okay. So just the numbering may not be the same, but some V2 I2 comma something has to be used there, maybe it is 1, maybe it is 2, maybe it is 3, I do not know, depends on how the rows stack up, okay. So likewise here I will use Vi3, I will put a question mark, some guy here, similarly here also, okay. So the main point here is the first row connected to the first bit is connected to I2, I3 so on. Now this I2th bit does not have one estimate Ri2, it has several estimates for each row. I will use the corresponding estimate suitably and compute my new estimates. Okay. So, I have a way of going from V to U, and then what will I do? I can also go from U to V, and then I can keep on repeating these iterations. Okay, so of course the question is when to stop. They stop changing. Okay, so of course, I mean all these are, in fact several people published papers saying when to stop, but all this was active 10 years ago, so you can't do that now. If you do that now, nobody will publish it. So one condition is you have estimates for all the bits, but nothing is forcing them to be a code word. Okay, so one simple thing to do is compute h times your estimated word transpose. If that ends up being 0, you simply stop. You got a code word, you stop. That's one idea. Okay, but that may not happen. You might end up in a situation where you never get a code word. Okay, so what happens in practice is there's always a limitation based on your complexities. You cannot do more than, let's say, 10 iterations. So you do for a while and then you just stop. You know, just decide I will output whatever I get after 10 iterations, for instance. Okay, so that's the way to do it. All right. So we are really getting close to the end of this lecture, so I will stop now, and then we will see the similar description on the Tanner graph. Okay, so and you will see the picture becomes much more clear and easy, etc. And the other thing to keep in mind is, I was talking about using one code word of the dual, using multiple code words from the dual. Okay, but it looks like in the way I described it, you are using only those code words of the dual that are in the parity check matrix itself. Okay. So stare at it and tell me if that's correct or wrong. That's actually wrong, using all kinds of other code words also, but does it seem clear to you that I am using more code words than those in the dual itself? Okay, yes, why is that?
The VIs brings in.
Exactly, because see, I think about it, so I am using several XORs, and that XOR is happening kind of in the way I am avoiding the same row, you know, that's the kind of idea to keep in mind. Okay, so I will come back and explain that also. That also will be very, very clear in the Tanner graph. In the matrix it's a little bit more confusing, but you can still see it. You can see how more code words of the dual are being used than that are there in the matrix itself, and this multiple iteration is key in doing that. Okay, so that's what helps you do that. Okay, so we'll stop here for now, take a break and pick up from here.